Hello everyone, we are Group 6. My name is Hiren and my other teammates are Arpit and Jesh. Today we are gonna present our research on three different security vulnerabilities. Our first vulnerability is prototype pollution with remote code execution in a software called Kibana. Well, Kibana is an Elasticsearch engine which runs combined with Elasticsearch and it pulls data from the Elasticsearch and shows in a visualization dashboard of the Kibana. The reported vulnerability severity was 10, which is very high, and the affected versions were our earlier version of 5.6.1 and a specific 6.6.1. The vulnerable parameter was timeline visualizer. And to start with a basic introduction of the prototype pollution of the vulnerability. So, well, prototype pollution means overwriting the properties of object. And when there is a bug in an application where an attacker is able to pollute the code by overwriting the object or prototype, or we can say pollute by polluting the object or prototype with the different arbitrary values. For example, take this application where object.prototype is admin is set to true and user is defined null. So every time attacker is asking to a application user.is admin, it is returning a true, which means attacker can act as an administrator and perform all the attacks. So this is what a prototype pollution. Well, to move further, confirming the vulnerability. So in the this is the dashboard of the Kibana and the timeline visualizer tab of the Kibana where data's level are set using this props level equals to abc command, and this command was modified a little bit to confirm the vulnerability, and where the object x was added with the proto to check the object's prototype, and when these commands get executed it turns out to be returning the prototype of that object x, and which is actually x. And to move further, what attacker does is he opens a Kibana in a inspection mode, and he says that the logs are generating and stating that address is already in use, which means Kibana is trying to spawn a new process. And to confirm this one, attacker opens a Chrome inspect, and in that he tries to observe the child process dot spawn, and there was a one command, or the we can say there was a one piece of code which normalize spawn arguments, which means it is trying to spawn a new process. And to confirm this one whether it is actually doing or not, what attacker does is it tries to create a new sub process using this command, and it tries to pollute the environmental variable by assigning passing a value 1 2 3, and when it is getting executed it's showing the actually this value 1 2 3 when the cursor is highlighted on options to the environment variable, which means every value which is passed to this environmental variable it is storing. So this is a where prototype pollution concepts come. This is a snippet code of the. Now coming to creating a payload. So what actually attacker does is he uses two environmental variables, and in the first one he tries to open a TCP connection at port number 12345 with his host IP address, and he's trying to acquire a new process. And to do so, like to make this environmental variable stored value code command to valid JavaScript, he loads the environmental variables from this given directory, and when this combined together it turns out to be valid JavaScript code. Now for the demonstration purpose I have a short video for you guys, and here in the demonstration we can see that attacker loads the payload in the timeline input, and he opens a TCP connection at port number 12345, and once he is executing that one and he is opening a canvas tab, it is actually executing and opening a reverse bash shell, and when attacker is typing ID it is returning a user ID of a Kibana for that attacker. Now this is the exploitation part, and the impact of the vulnerability can be once the reverse bash shell is established, attacker can read all the files stored on the server. And to escalate this vulnerability further into the privilege escalation, Attacker can use getCap command to list all the capabilities of that system where the server of the Kibana is running, and he can set user ID from 0 to 0 from any random user ID or set or 1000 to become a root user and can perform all the malicious actions. Now to coming the mitigation part, the mitigation can be done in three ways. First, upgrading a Kibana to its the latest version of the 7.1 or any further versions, or if a user is not able to do so, he can enable expect.security.audit to true by going to kibana.yml file, and by doing that it will start generating the logging events, and SOC team can analyze the logs and detect this attack. The third page can be like here in this piece of code, cursor.has on property.prop, which means it will every time when the value is passed, it will check that whether it is a actual or prototype of the object or not. So it will sanitize the input and it will try to prevent the prototype pollution.
Hello everyone, I am Arpit and now I will continue with the presentation. To discuss further, second vulnerability is breaking out of Docker via runc, and CV for this vulnerability is 2019-5736. The severity score for this vulnerability is high, and that is 8.6, and affected software for this vulnerability is Docker. Docker is an open source software and is a set of platform as a service products that use OS level virtualization to deliver software in packages called containers. And the affected version of the Docker is 18.9.2 and earlier version of that. When talking about impact of this vulnerability, a malicious actor who creates a specifically designed container image can get administrative access on the host by exploiting this vulnerability. So, what is runc? Runc is a container runtime originally developed as a part of Docker and later extracted out as a separate open source tool and library. As a low level container runtime, runc is mainly used by high level container runtimes, for example Docker, to spawn and run containers, and although it can be used as a standalone tool. And high level containers runtimes like Docker will normally implement functionalities such as image creation and management, and will use runc to handle tasks related to running containers. For example, creating a container, attaching a process to an existing container, Docker exec, and so on. To understand the vulnerability, we need to go over some proc basics. So the proc file system is a virtual file system in a Linux that present information basically about processes typically mounted to proc, and it is virtual in a sense that it does not exist on the disk, but the kernel creates it in memory. Now let's talk about what is the vulnerability. This vulnerability affected all container engine running runc from version 1 to RC6. The vulnerability allows a malicious container to access root level code execution by overwriting the host runc binary. And malicious container could overwrite the host binary with minimal user interaction. To execute code as a root within a container, users were only supposed to run commands either in the following context: creating a new container using an attacker control image, or attaching Docker access into an existing container which the attacker had previous write access to. These two scenarios might seem different, but both require runc to spin up a new process in a container and are implemented similarly. In both cases, runc is tasked with running a user-defined binary in a container. In Docker, this binary is either the image entry point when starting a new container or Docker access argument when attaching to an existing container. This is the method used by runc both for creating new container and for attaching a process to an existing container. Now to move further, confirming the vulnerability. When runc attached to a container, the attacker can trick it into executing itself, and this could be done by replacing the target binary inside the container with a custom binary pointing back at the runc binary itself. So for example, if the target binary was bin base, this could be replaced with an executable script specifying the interpreter path, number sign explanation mark, and proc self access. This syntax is called sebang and is used in script to specify an interpreter. When the Linux loader encounters the sebunks, it runs the interpreter instead of the executable path. So as you can see in the code, the attacker can then proceed to write to the target of proc self access and try to override the runc binary on the host. When the runc process is executed in the container, those libraries are loaded into the runc process by the dynamic linker, and it is possible to substitute one of those library with malicious version, and that will override the runc binary upon being loaded into the runc process. As you can see, Dockerfile builds a malicious version of the libsec-comp library. Now the Docker file appends the content of run at linc to one of libsec-comp source file, and as a result the malicious libsec-comp is built. As you can see in the code that the constructor attribute GCC specific syntax indicates that the runAtLink function is to be executed as an initialization function for libsec-comp after the dynamic linker loads to the runc process. Since runAtLink will be executed by runc process, it can access the runc binary at proc self-x, and the runc process must exit for the runc binary to be writable though. To enforce the exit, runAtLink calls the execsys call to execute override runc. Now moving to impacts of this vulnerability. This vulnerability allows a malicious container to access root level code execution by overwriting the host runc binary. If the attack is successful, the attacker will gain full control of the host and can try to attack resources in the internal network segment, and this can allow an attacker to deploy a malicious container inside the production environment. And then if in a production environment, this attacker has access to an existing container, allowing software deployment and giving the attacker the ability to execute script inside a running container. Now let's look at some mitigation strategies. The first one is upgrading Docker to the latest version of 19.1 or any further versions will mitigate this vulnerability. The second one is to prevent this attack. runc has been patched to create a temporary copy of the calling binary itself and when it start or attached to the container. So to do this, runc creates an anonymous in-memory file using the memfd create function and then copies itself into the temporary in-memory file. As you can see here, it generates memfd create system call, which is then sealed to prevent further modification of the file of the host runc binary file. Now any compromising write operation from a root container to the host runc binary file and then write to the temporary file, not to the host binary on the disk. So we can say that it preserving the integrity of the host runc binary file, and it will not allow any changes or modification to the host runc binary. So these are some of the mitigation strategies that are used to patch this vulnerability.
Hello everyone, I am Jash Patel and today I am going to present the vulnerability of an open source project that is Apache Tomcat. This vulnerability is named Remote Code Execution in CGI Servlet of Apache Tomcat, which is also known as CVE 2019-0232. According to the National Vulnerability Database, the rating of the severity for this vulnerability is given 8.1 out of 10, which is pretty high and can be considered a matter of concern for the software. The versions that were affected because of this vulnerability are shown here. Basically, these were around versions 7, 8 and 9. The primary concern of this vulnerability was the remote code execution on the machine using the web-based CGI servlet. That is, while using a CGI servlet for inserting the command for Apache Tomcat, if an attacker executes an operating system's command, it would get executed on the machine. This basically creates a threat to the information inside the machine, which becomes open for the hacker to get it using the vulnerability. Here, the CGI means the Common Gateway Interface, which is a standard protocol to allow any web servers to execute command line programs using web request. This protocol also allows passing command line arguments to the script or program being executed via URL parameters. The vulnerability exists because of this URL parameter part. Apache Tomcat supports the execution of CGI scripts in a non-default configuration via a special CGI servlet. This servlet also passes URL parameters and translates them into command line arguments. As you can see here, the web URL has the end part such as test.bat and the parameters are dir. But what is being executed is shocking. This is the command of the Windows operating system to view the list of files and folders in the directories. When CGI support is enabled in Apache Tomcat in Windows and command line arguments passing is enabled, it is possible to cause command injection via parameters interpolation when calling a batch file. This happens because CMD performs interpolation on some special characters before execution, which can cause other shell commands to be called. Neither Apache Tomcat nor the Windows GRE performs any kind of input validation for these special characters. So basically, when the parameters enable command line argument in the config file is set to true, this vulnerability is exposed. Here is the web.xml file from the source code. As shown here, when the parameters enable command line arguments is changed to true, it becomes possible to pass Windows command to the URL. This particular way was suggested by the developers of the Apache Tomcat to mitigate the problems temporarily. That is, if you want your computer to be safe from unnecessary exposure, just need to go to the web.xml file and change the value of parameter to false to avoid problems. The developers later revealed that the problem is there were no proper validations done for the command that is being considered as an input for the CGI. The program was not able to distinguish the commands entered as if they were for the Apache Tomcat or for the Windows. As you can see in the code below, the variable command is appended as it is without any proper validation and sanitization. This is the reason the Windows commands were being executed from the URL directly. Now let's look at the changes done to patch this security issue later by the developers. The given code is the later version of the Apache Tomcat's code. It is clearly seen that if the GRE platform is Windows, the commands are being matched to the particular pattern before being forwarded and executed. The developers declared that this was a minor mistake in code which led to a huge vulnerability exposing the system where the software is being executed. Now let's have a look at the impacts. This vulnerability had all the three crucial impacts that are confidentiality, integrity, and availability. As the information is being revealed by passing commands, it compromises confidentiality. Attacker can also modify the information and can also retrieve unavailable information from the system, which results in integrity and availability issues. Some attackers can easily insert the virus into the system by passing some Windows commands and can also run some process which can later result into denial of services. The impacts were high as seen from the given table. As discussed earlier, the vendors provided two major fixes. The first one was changing the enable command line arguments parameter, and the second one was adding a new parameter to the config file, that is command line arguments decoded. This parameter will validate the command given in the input before executing it, as if the command is for the CGI or it is for the Windows. If the pattern matches and shows that it is for the Windows, the further execution of the command will be aborted and the system will be safe. Here the patterns are shown for the Windows and other operating system that needs to be matched for the validation for the input commands.